All right, let me get the share screen going and we'll go over worksheet 6 on magnetism. So it looks like we're good to go. Just gonna dive in right here. Just a few quick announcements. First is, if you're watching at home, can you just QR code it up? And then also, this is a link. Obviously, if you're watching the recording, like you can't click the link through the recording, but this is just like the SI evaluation that I sent you. So just fill that out if you can. Like, it really does help me out, and I get to like get a feel for like what everyone's saying, and it like helps me adjust things. Just like even just off the cusp, what I'm gonna change is going forward is like for the midterm 2 review, it's gonna just be a bunch of questions that are midterm style and less like explaining the concepts. It felt like the most helpful part of my review was when I was doing those problems that were of interest. Other than that, I think we're good to go. Oh, let me first thank you guys for your patience on last week's worksheet. So the syllabus is off now. We're like off track here. So when I introduced like Faraday's and Lenz's law for worksheet 5, that was incorrect and people were confused about it. And I was like, oh, maybe like the classes are different schedules, but it turns out we're just like a little bit behind. So basically ignore worksheet 5. This is worksheet 6 on magnetism. This is going to be going over what we did last week. All right, let's just dive right into it. So here's our equations, and I just wrote out like the long subscripts for each one just because I feel like it can get kind of confusing of when you're working with what. So I think the most important thing is to just be able to identify. Let me just make sure I'm not muted here. Yeah, it looks okay. Yeah, we're good. So it's just like to identify when we're dealing with a charge versus a wire. Obviously, when it's a point charge, it's going to be like an electron or a proton or something that's like that's moving, and or versus the wire. I'm sure like you guys know. Obviously, like there's different right hand rules applied to each. Where let's say for the charge, we're like pointer finger, middle finger for the magnetic field, and thumb for the force, and then versus like with the wire, like we'll use like if it's like we're using our thumb for the direction of the current, or more likely it's like our fingers in the direction of current and then your pointer finger goes the other way. And then the same thing can be applied to the forces here. And this is just our equation for force per unit length. This comes up, and we're going to do an example on that. And then just of a solenoid. We go over that so much, but we don't really get that many examples, but we talk about it a lot. So I think that just help. This example will just kind of establish a property of solenoids, but more on that later. Magnetic moment, I included that in the off chance you would need it. It's unlikely. And then obviously this is our mu naught constant. And then, force charge and then a force of a wire on a wire. So here are our right hand rules. This is just the way I think about it, like for all 4 of them. This is like, curved wire, straight wire, force on a charge, and then force on a wire. The only things I want to point out here are for like curved wire, we're going to be talking about like when something's wrapping, like solenoid when we're looking there. And then on a charge, we always assume the plus charge. So like, when you're like, let's say it's moving, how should I do this? I don't know if it's moving this way and our like field's going where my middle finger is pointing. So for you guys that looks out, but I'm actually pointing in and my thumb's pointing up. Like that's always in relative to a plus charge. So in case it's like an actual electron, like to flip that, right? We went over that. Other than that, yeah, I'd say like just be careful of how you denote each one. And I think that let's just like dive into these kind of key idea examples. So in number 2, these are just very light general. We're going to be determining the magnitude and direction of the force of an electron that has a given velocity and to the right of a magnetic field with a 0.45 strength, and it's pointed upward at an angle. So what equation do we use? We're going to be using that F subscript charge with the equation being, oh, I forgot I can't move these things when I'm on present mode. With our equation being QVB sine theta, where that theta value angle right here is the angle between the direction in which it's moving and the actual magnetic field. So everything else is given, so we just plug everything in, right? Other than that, I just want to, like the main point of this question is just to like, what's this angle right here? In reality though, that angle is gonna often be 90. This is just in that off case. Unlikely, but yeah. So this next one's like a true or false situation. And this is meant to establish a concept that you guys need to be very comfortable with. So let's say we have this electron that's moving to the left. And we're asked, is there a way to point the magnetic field such that the magnetic force is shown? So we're normally used to, doing pointer finger, middle finger, and then thumb. But here we're asked to use pointer finger, thumb, and then middle finger. But if you have a good eye, you will know that this is impossible. And why do you ask? That's because the force needs to always be perpendicular to the B vector and then direction it's moving. So yeah, false. FB is always perpendicular to the velocity, the direction it's like moving, and B, which is not which won't be the case in this situation, right? Like this is obviously not perpendicular. Okay, so let's just look at this one now. This is kind of our real question here, first one of the type. So here we have an electron with an initial velocity, 1.5 times 10 to the 6 meters per second upward, and it is going to be moving, so it's moving up through a region with a constant magnetic field pointing into the page. So we're asked for a few things, but let's just start with part A. First is, what is the magnitude and direction of the magnetic force acting on the electron? And yeah, obviously you can see everything right here, but I want to explain it, and then you guys need to think through it yourselves too. Don't just take my word for it. So let's just draw our diagram. We first are going to draw, all these X going into the page in respect to the constant magnetic field. And we know the electron is traveling upwards. So what we're going to do is work with our right-hand rule, and this again is working with a charge. So, pointer fingers pointing straight up. Our middle finger points into the page. And my thumb right now, I apologize, I don't really remember how it comes out on Zoom, if it's mirrored or not, but just take my word for it. My thumb right now is pointing to the left, but obviously it's not pointing to the left here. And that's just because we do it relative to a plus charge. And when we're working with a negative charge, we switch whatever result our thumb gives us, we switch it the other way. Cool. So that should make sense why it's drawn like this. At this point, we know everything, right? We can plug in our Q, we can plug in our V, we can plug in our B. And then remember, sine theta, because here we're dealing with some perpendicular elements. I mean, sine 90, we're dealing with perpendicular elements. So then in part B, we're asked, what is the direction and radius of the electron's circular orbit? So circular orbit, that might be a little bit of a blast from the past. We're talking about 135A centripetal acceleration. I wrote that right there. But what should tip you off to think that? Again, it's circular motion. So when we include that, we need to remember a few properties of that chapter, namely like what AC equals, which is that V squared over R. And this, you should kind of be tipped off to use this equation because part of what we're solving, what we are solving for is the radius of the circular orbit and then direction in which that's happening. So now we have this expression, we just solved for that actually. And we have a force equation, so mass times acceleration, where acceleration equals that V squared over R. Everything here is known except for this R, so we're just going to do some rearranging. So we're going to multiply by R on this side, and then divide by this whole expression, that whatever FB equals, onto the right side of the equation here. So now we have an expression for R, and plug everything in, and we'll come out with this value. Second part of this is asking for the direction. So I wrote clockwise here, but the reason for that is, well, as you can expect, we have kind of a setup here where the electron is shooting straight up. And we also have that force going to the right. So combined, they're going to actually be moving on this angle in clockwise direction. It's going to be going in that circle. Cool. Next thing we're asked for the period. Just use period equation here. We now have a radius, so we can easily plug in. And we just solve that out, and the units obviously are seconds. The next thing we want to look for is, sorry, ignore the direction part, is what is the magnitude of the electric field that must be applied if the electron is to move through the region undeflected. So what does undeflected mean? That tells us that instead of having that clockwise circular motion that we discussed, we want to just keep going straight. So what do we need to do? We need to have an equal and opposite force acting against this FB. So I just want to call that FB. So we have an FE force now acting to the left. And for them to cancel out, obviously FB needs to be equal to FE. Otherwise, let's say FE is bigger, it would be favored going counterclockwise. Or FB is bigger than FE, it'd be favored going clockwise. But here they're set equal. And remember, FE equals QE. This is from like our first or second week. And then at this point, we're like, look, we're solving for that big E. So we just have to rearrange this equation slightly. And then we can solve for the applied magnetic field. Cool. So this one, I like this question because it's a culmination of a few different concepts. And it's just things to keep in your back pocket because, if it comes up, it comes up. All right, number 2. So I also like this one because it teaches you a property of finding where the magnetic field equals 0. So this question is obviously simple in this setup, but it can be made a lot more complicated. But the principle of it is something that I'd say is exam style. So, and that being like, if it's in a more complicated situation, how do you solve? And based on, I shouldn't say how do you solve, it's developing the intuition to kind of address these problems. And I'll explain. So we're given wire 1 with a 50 amp current going upward, and then 30 centimeters away is that wire 2 with a current of 20 amps going upwards also. So this is where it gets spicy, and that being we're finding where it equals 0, the magnetic field. So the part where I said you need to develop a sort of intuition is, where would that be? Would that be to the right of right of wire 1, left of wire 2, in the middle, on wire 1? Like, there's so many options. But the reality is, it will always be where there's these two fields canceling each other out. So let's first establish how we get those fields. I drew out my diagram, 30 centimeters apart, both of my currents going upwards. At this point, I'm going to use my right-hand rule when I'm dealing with a wire. One of the, I forget which number I called it on the first page. Straight wire. So that's right-hand rule, letter B. My thumb goes in the direction of, my thumb goes in the direction of the current. So I'm going to go like that. My fingers curl, and they'll tell me how the field's acting at which point on both sides. So now in respect to I1, I'm going to be doing camera and trackpad at the same time. So prepare for multitasking. My fingers are going into the page. And then on the opposite side right here, my fingers are now popping out of the page. So now I've established with respect to I1, here I have a magnetic field going in and popping out. And same business right here, in and then out. So now, where would this be? Obviously, I'm telling you, you see it here, it's in the middle, but why? Let's say we thought it was here and why that wouldn't be. So here we have by I1, the field's going in, and by I2, it's also going in on that side, right? So both fields going in on to the right of this I1 of wire 1, that tells us, no, wait, that thing's not going to be there. And then the same logic is applied here. With respect to wire 2, there's that field that's coming out. And then also with respect to wire 1, this guy will also turn and it'll be coming out here too. So no way will the field equal 0 on this side or this side. Therefore, it must be in the middle. So for them to equal 0, obviously they need to be equal to each other, where the difference being the current or and the radius. These guys are all constants between them, right? So I cancel all that out. At which point I can define a distance x from wire 1. And realistically, you can like choose wire 1 or 2, but I like defined it to the left of wire 1. But like, if you can work either way. And now I have I1 over R1 and then I2 over R2. We know I1, we know I2. R1 is what I'm going to call this distance x. And then what's R2? It's just this total distance they're apart minus x, right? That's just your algebra. Just solve this equation now, and you'll get 0.214 meters to the left of wire 1. Cool, right? And then the same thing, same thing right here kind of with this one. Here, I can go back to present actually. But you can still see my mouse, huh? Yeah. Okay, so same thing with this one. Wire 2 now carries the same 20 amps, but downward. Where's the magnetic field equal to 0? So this is a different situation. You need to redraw every one of your fields relative to the positions and reconceptualize. Otherwise, you're going to get it wrong. Like obviously, we know it's to the left here. And also, we're dealing with wire 2. I wrote that up at the top. So, I mean, the reality is wire 1 stays the same. It's in and then out. Wire 2, now thumb's pointing downwards. It's going in and then out. So in on this side, out. And then I'm going to draw the forces. Excuse me, not forces. Let me rewind. And now I'm going to draw the field by wire 1 on 2 and 2 on 1 with purple. So wire 1 on 2 is now coming out of the page on this side. And then wire 2 on 1 on like one side is going into, is going out of the page, right? So thumb, I rotate, and it's coming out of the page. So now we're looking where it equals 0 on this side. Obviously, it's going to be here because here we're going to have some cancellation. So again, same setup, except now this distance, sorry, I skipped the algebra here, but that R1 that previously was associated with here is now 0.3 plus x, because it's 0.3 and then plus a distance x, right? And that's 0.2 meters to the left of wire 2. Okay, so yes, over here this looks easy and it seems very straightforward, but this could be applied to a multi-wire situation where wires are going, like there's like 3 in a triangle and there's angles and all this stuff. So the important thing to establish from this is an intuition on where they will be canceling out, that being between, or basically where you have, the equal and opposite effect from the field, right? And like obviously, if you pick the wrong spot, you'll end up solving and you'll be like, wait, this doesn't come out right. So that will kind of like save you time. Anyway, I think it's just good to establish that. Okay, let's move on to question number 3. And this is our solenoid question. And again, this is demonstrating a principle of solenoids. So here we have a 314 centimeter long wire shaped in a solenoid with a 10 centimeter diameter. The current is 4.5 amps. It's produced through the wire. Each circular turn of the solenoid has a width of 1 centimeter. So the first thing we're asked is, what is the magnitude of the magnetic field of the solenoid? So what equation are we using? Obviously that solenoid of magnetic field of a solenoid equation that I gave you. What was that? Equation number 6 on the first page. So there's a few elements we don't know here. Obviously mu naught is a constant. I lost my mouse. Oh, here we go. Mu naught is a constant. N we do not know. I is a given. And L we do not know. So the first thing, let's just find N. So here I converted the total length into meters. Next, I'm going to use the circumference of a circle times n. Why circumference? Because each one of these loops is like the perimeter of a circle, right? So circumference, 1, and then 2. And that times n needs to equal that whole length. We do all this math, it comes out to be 10 loops long. The next thing I want to do is find that little L. So I'm going to take that 10 and multiply it by the width of each loop. Now I have 0.1 meters. At this point, all I have to do is plug in. I get 5.65 times 10 to the minus 4. All right. Next thing, we're going to have the same wire. It's stretched and twisted tight so that it has a new diameter, smaller diameter. So what's n? As you would expect, by the diameter becoming half, the length of the wire is, it's like intrinsic to the wire. It's not going to be growing or whatever. It's like stuck there. So it's going to have twice as many loops. Again, you can just solve that with the arithmetic. And then the length between each, the little L we're solving for now is just going to be that 20 times that distance between each loop, 0.2 meters. At this point, we just have to plug back into our equation, and you'll see that it comes out to be the same thing. And that's kind of powerful because it informs that there is a proportionality between the number of loops and that little L, where but this guy goes up by 2 and this guy goes up by 2. They're obviously they're like on opposite sides of the division, so they'll be able to cancel out, and then that value will actually be constant. So keep that in mind. All right. Also, just remember how to find this value of big N, because it's kind of seems like it could be against your intuition. All right, last one. So here we have 3 long parallel wires, and they're all 4 centimeters from each other. the current in each wire must be equal to each other and is initially 8 amps in the direction shown below. Determine the magnetic force per unit length on M due to N and P. If the weight of the wire M is, 20, what must be the current in each wire to levitate the wire M? All right. So let's first start with, how should I explain this? Okay, let's just do the magnetic force per unit length. So we have a few forces acting on this, or here's that position M. Let me explain my angles too. We know that if I just cut this right here, this is a right triangle where it's actually a 30, 60, 90 triangle, right? Where that's 30 degrees. Thereby, by like the alternate interior angles, that's also 30 degrees right there. Okay, we know what theta is. We need to be able to make it such that FP is equal to Fn. Otherwise, like if Fn was greater than Fp, like we know this wire right here would be floating upwards to the right. We know that's not the case. We know it's stuck here. Additionally, we know that the x components of both of these forces cancel each other out. They're equal and opposite per the fact that they have the same current and they're the same distance away and the rest are constants, right? So there's actually those x components of the force, but we don't have to worry about them. They cancel each other out. What we do have are overlapping, like right along this axis, are y components of both of these forces, where these forces are those of a straight wire, right? So you can just say Fy equals that Fpy and that Fny. So those are the y components of both of these forces. Since they're actually all the same, I'm just going to add them together. And then we have an expression such as this. Okay, and this is that force per unit length equation, where we have the two different currents. But here, they are the same currents, so it actually works out nicely that we can just write I squared if you wanted to. But yeah. At this point, what we have to do is plug in that mu naught. Well, I think I might have forgotten a 2 here. Yeah, this is multiplied by 2, right? Because it's right there. Just keep that in mind. Multiply this by 2. Oh wait, no, I'm sorry. Actually, the 2's canceled out. That's what I did. Okay, so this is fine as is. So we have 4 pi times that constant, 8 times 8, and then cosine 30. That's that angle right there. And then pi times that distance they are apart. At which point we get a force, a value newtons per unit length over meters. And then we're asked if the weight of the wire is, as they gave us, what must be the current in each wire to levitate it. So now we need to work for a current, given that this wire is no longer considered. We have to deal with its weight. Its weight being that force of gravity pointing downwards. So we know that the force of gravity per unit length needs to be equal to that force by these two currents, by these two wires per unit length. So that expression. If we open up this, as you recall, it's equal to mg. You remember weight equals mg, again over that unit length. So here, we're going to use that same equation. It's basically what we used up here. We're going to get square root, and we're going to be solving for I this time. Because I is now like what do the currents need to be to levitate it if it has this weight? So at this point, we just have to plug everything in. Oh yeah, okay. So yeah, they gave us the weight here as 20 grams per meter. So we're given a per unit length, but just convert that grams to kilograms. So 0.02. And then you'll get your current that needs to go through both of those wires such that it can levitate that wire right there in the middle. All right, awesome. Ooh. So that is it for the worksheet. Pretty quick recording here. Yeah, I'm gonna now do a separate recording for one of the homework questions the student asked me about. So if you're confused on homework number 6, number 3, take a look. All right, guys, thanks for watching.